Okay, so welcome everybody to another exciting talk on in the Crypto Cafe. Unfortunately, those of you who are online cannot enjoy the nice chocolate cake that was provided today, but so it's our pleasure to have Zhenisbek Assylbekov, a former colleague of mine who has been working in a very interesting direction of applying grading-based methods for learning to prod the security of well-known primitives. So thank you very much. The floor is yours.
Thank you, Francesca, and everyone for giving me this opportunity to talk about failures of gradient-based methods on the task of cracking AES. So I'm currently at Purdue University Fort Wayne, and my co-author here, Kanat, he is a former research assistant from Nazarbayev University, where I was working before joining PFW. And yeah, Francesco was also working at Nazarbayev University. Actually, he knows this problem because I started working on it quite a long time ago, like I think 2 or 3 years ago. And I often asked Francesca some basic things about cryptography. My background is in statistics, and now I'm more involved into machine learning research, and usually I apply machine learning algorithms to text data, to language data, and this was sort of a side project at the beginning, but then I became interested, and yeah, I hope we did some contribution. All right, so let's start. There will be 3 parts, and first I will say about the connection between machine learning and cryptography. Then I will give details on the cryptographic primitive that we want to try to crack with machine learning, and then finally, I will try to explain why gradient-based learning fails to crack AES. Okay, so we will consider a very typical supervised learning setup in machine learning, where we have inputs, X's, and outputs. So in this case, images are of fruits as input, and name of the fruit, so-called labels, are outputs. And we have a collection of such examples, which we call training data, training sample. And then such data is fed into a learning algorithm, machine learning algorithm, whose output product is a function, which maps X's to Y's. Okay, this is what we want from the learning algorithm. At the end, we want a so-called classifier, which upon receiving any new image, not necessarily from the training data, but arbitrary image of a fruit, will produce a correct label. That's our expectation, what we hope to get. And of course, the percentage of correctly classified examples on new data is usually the measure of success of the learning algorithm. Now, also feel free to interrupt me at any time. I think we have plenty of time. We can consider as inputs and outputs objects of arbitrary structure. So, for example, inputs can be sentences in one language, and outputs can be sentences in the other language. And then if we treat this again as a supervised learning setting and feed this training sample into a machine learning algorithm, at the end of the day, we want to have a so-called translation model. And this model, F, upon receiving a new sentence in the source language, which wasn't necessarily in the training data, is assumed to produce a nice translation to the target language. Okay. Now, if you don't know Croatian, then the first column here, the column of X's, may seem to you as a ciphertext, as encrypted text, right? And Y as plain text. And this is exactly my naive hope a few years ago that I knew something about machine translation, especially neural machine translation, which was booming back in 2017, 18, 19, 20. And I thought, okay, I know how to train such models, then why can't I apply it to cryptography? And let's say a few words about symmetric cryptography. So suppose you have a plain text, a message that you want to send. So it's not necessarily text. It can be any data, images, sounds, video, whatever. And you want to send it to a friend, and you and your friend you share the secret key. And then you apply some secure modern encryption algorithm parameterized by the secret key. And this gives you a ciphertext, which is sent to your friend, but the friend knows the secret key. She applies the inverse of the encryption, and encryption is assumed to be one-to-one correspondence. So she applies inverse of encryption, which is decryption, and then gets the plain text and can get the message. Okay, so I thought, why can't I apply the translation approach to this part? Why can't I generate many plain text and ciphertexts, corresponding ciphertexts, and treat them as something written in foreign language and something written in the language that I want to translate into? Okay, so let's try. Let's take some text. Again, it doesn't have to be text, but just I was working more with text. So we take some text. Of course, we take the binary representation and encrypt it using a fixed key. So we use fixed AES, and I will explain what AES is. So we use encryption algorithm with a fixed key to encrypt these sentences. Good. And then we apply. We feed this into a machine learning algorithm. It gives us decryption model. And then we say, okay, why don't we apply the result of learning this decryption model to a new ciphertext? Because this is what we want to do. We want to decrypt encrypted messages, right? Okay, once you do so, it gives you garbage. It doesn't. The learning algorithm fails to produce you any meaningful decryption model. And then I started to dig deeper what was going wrong, and consider a plain text. The sentence: "The quick brown fox jumps over the lazy dog," and it's encryption using AES with fixed key. And then let's take this lowercase f and change it to capital F. Okay. So if I was translating this into human language, then the corresponding translation wouldn't change much, right? However, with encryption, with ciphertext, it's completely different. So it seemingly has nothing to do with the original ciphertext. So good encryption is not predictable, and this is intuitively what prevents machine learning to crack these functions successfully. So now we get to the main hero of this story, advanced encryption standard. So it's probably most widely used block cipher nowadays, and it takes at input blocks of 128 bits and produces at output blocks of 128 bits. It's a one-to-one function, and it is parameterized by a key, and the key length can be different from 128 to 256. Yeah, it was developed in late 90s, and it's, as I said, it's most widely used block cipher nowadays. It's used by each of us every day when we surf internet, when we send email messages, when we communicate in messengers, and here in Zoom. And interestingly, it's not based on any hard mathematical problem, unlike public key crypto systems, or at least we don't know there is one. And state-of-the-art attacks, nevertheless, are only marginally better than brute force search of the key. So I will give a few more details about AES. And we can think of AES as a special case of substitution permutation network, which in turn is a special case of the key alternating cipher. So first I will explain key alternating cipher, and then how SPN specializes KAC, and then how AES is a special case of SPN. So key alternating cipher is a fairly straightforward thing. It takes at input an n-bit binary, n-bit string, adds key. So this is XOR operation. Key is let's, for simplicity, assume key has the same length, also n bits. And yeah, of course, in case of AES, n is equal to 128. So you can think of n as 128, and the key is also 128. Let's consider like the simplest case. So the key is XORed with the input, and then permutation bits are permuted. And then another key is XORed, and another permutation, possibly another permutation is applied. And so on and so forth. This is repeated R times. R is the number of so-called rounds. Okay, so how SPN is a special case of KAC? Well, SPN assumes that this permutation has a special form. So it assumes that the input, these n bits, of course, after the key was added, right? So we look at 128-bit string, which is a result of taking original input, adding the first, like the zeroth key. Okay, now the input to permutation is divided into like sub-blocks. Each of such chunks is, say, b bits, and each such chunk is processed by a nonlinear transformation S, which is usually called S box. So these chunks are transformed by S box, and then they are concatenated together and fed into a linear function, and the result of linear function is the result of this permutation. And now AES specializes SPN in basically saying that B equals 8, so 128 bits are cut into pieces of 8-bit. Now each 8-bit chunk is processed by the S box, which has particular form. It's an inverse in the Galois field of order 2 to the 8. So this 8-bit string, binary string, is treated as element of Galois field of the order 2 to the 8, and in that field, if the if the element is non-zero, there is an inverse. So that inverse is the result of S-box. Yeah, it's so-called patched inverse, right? So for zero, it produces zero. Okay, so we can think of AES as a sequence of non-linear and linear transformations alternating with addition of the key. We may wonder why we need S, non-linear transformation, and why we need linear. Well, the non-linear transformation, as far as I understand, it's so-called confusion. It hides the relationship between key and the resulting ciphertext. Otherwise, if everything was linear, then methods like differential cryptanalysis could be used to recover the key, for example. The linear layer is needed to do so-called diffusion. It's when one change of one bit before linear transformation is applied results in change of, say, half of the bits when after the linear transformation. So here's an example. Say this is the the input. Well, only 8 bits. We apply the block cipher with nonlinear and linear transformations, and this is the result. And say we change just one bit, and we expect approximately half of the bits to be changed. Okay, now and now we switch to why is it impossible to crack AES with gradient-based machine learning. Do you have any questions so far?
How many rounds of those S-box and linear transformation would do general?
Oh, sorry, I can barely hear.
In the graph, it shows 3 rounds. What's the general round we use for this kind of transformation?
How many rounds in AES?
Ah, right. So this is important. In AES, so AES, depending on the key length, can have either 10 rounds for 128-bit key length, 12 for 192, and if I remember correctly, 14 for 256. So in the simplest case, yeah, 10 rounds are used in AES 128. Yeah, the number of rounds is important. It will be. It's actually one of the limitations of our result. Okay? I will need to say a few words about indistinguishability, computational indistinguishability. So suppose you have 2 images, 2 pictures, and say I ask you to find any differences, and I give you a limited budget in time, say 5 seconds or 10 seconds. Now, chances are that within short period of time, you will most likely not find a difference. But if I give you more time, say 1 minute, 2 minutes more, when you carefully inspect these 2 images, you can find some small differences. So can you see my mouse when I move?
Yes.
So yeah, yesterday I double checked, and I think this here and here are sort of a little bit different, but of course it requires, right, some time. So this idea can be used to try to define computational indistinguishability. So we will talk about probability distributions. Say we have 2 PDFs, P and Q, and suppose there is an algorithm D, and it's a decision algorithm, so it outputs either 0 or 1, and it is supposed to distinguish samples from P and from Q. So we expect B to produce different outputs, at least in many cases for samples from P and from Q. And then we say that two distributions P and Q are epsilon close computationally if this expression, so the probability that B accepts on a sample from P and probability that D accepts on a sample from Q. So these probabilities differ by no more than epsilon for any polynomial time algorithm D. And this expression here, the difference between two probabilities, is called advantage. So this is the closeness, okay, the closeness of two distributions computationally. Now, what we know about AES is that if we take two different inputs to AES and pick a random key, so suppose we pick purely random key and we have two fixed inputs, then if we apply AES to these inputs, we have outputs, y and y prime. Now, the thing is that these two outputs, which are two strings, two binary strings, so these two outputs will be this close to 2n-bit string, like 256-bit string, such that half of, like the first half and the second half are like purely random n-bit strings distinct. Okay, so in short, the output of AES when R is sufficiently large, but sufficiently large here is, of course, like if we want this number to be 2 to negative 128, R should be in the order of 1500, which means AES with 9,000 rounds will be, according to this result, secure enough. Okay, this property is called pairwise independence. So okay, this was shown in the crypto conference in 2021, and we will rely on this result. So suppose we wanted to solve a simpler task. Okay, say we don't want to learn the full AES. Let's suppose we learn just single bit. Without loss of generality, we can think of the first bit. So consider this function, which upon receiving x input, and x is in binary string, gives -1 if the first bit of AES is 1, and +1 if the first bit of AES is 0. So it's essentially first bit of AES just rescaled. And for this function, it's clear that on average it's 0, because of course if we go through all possible binary strings of size n, then at the output, since AES is permutation, at the output, half of the outputs will have 1 as a leading bit, as the most significant bit, and half of them will have 0. So on average, this gives us 0, and variance is 1 simply because the second moment for this function is just 1, and the average is 0. And now we can show the following result, that if we take a pair of distinct keys, key and k and k prime, and arbitrary epsilon, then we can find number of rounds in AES such that the correlation between Fk and Fk prime is small, or you can think of this as inner product between Fk and Fk prime. So these are two functions which are formed as first bits of AES, just with different keys. And now such functions seem to be nearly orthogonal or nearly uncorrelated. And this, of course, is based on the result on the result of Liu. The drawback here is, of course, that R is unnecessarily should be unnecessarily high, as like 9,000. But of course, in reality, 10 rounds of AES are usually enough. Okay, so there is one remark. If we had purely orthogonal functions, so if this inner product, this correlation was exactly 0, then we could use the result of Shalev-Schwartz from 2017, who showed that for such classes of functions, which are purely orthogonal, gradient-based methods inevitably fail to learn an arbitrarily picked function from this class. So unfortunately, we don't have pure orthogonality. We have near orthogonality. And I remember approximately 1 year ago, I started approaching my colleagues at NU, asking, okay, I don't have orthogonality. And in the proof of Shalev-Schwartz, the key ingredient is Bessel's inequality, which is true for orthonormal systems. But I don't have orthonormal systems. So I was asking people if is there any analog of Bessel's inequality, but for nearly orthogonal system. And it turns out that well, I found it myself. It's so-called Boas-Bellman type inequality. So suppose you have an inner product space and elements from this inner product space, F1, Fd, and G is also an element there. And you consider these projections of G on Fi's, and you square and you sum up, and then the result is not exceeding this bound, which, if you think of Fi's as assume they are orthonormal, then of course these pairwise products will disappear, and the norm here is going to be 1. And this whole bracket basically becomes just 1, and then we get the classical Bessel's inequality. Now, once they are not purely orthogonal, orthonormal, we have this price we need to pay for not being orthonormal system, and we essentially used this instead of Bessel's inequality in the proof of Shalev-Schwartz. And okay, so what is our task? Our task is to try to learn this function using, of course, the supervised setting that I described at the beginning of the talk, and in some class of parametric models. So suppose you have some deep neural network which has millions or billions of parameters, theta. So theta here, vector of parameters. It's in modern deep neural networks, it's in order of millions, billions, sometimes trillions. And we want to approximate this function, this original single bit of AES, by a neural network or any other parametric model. And of course, we want to do this based on SAM. So we will generate many plain texts. We will encrypt those plain texts And these plain texts are, of course, 128 bits, right, written in hexadecimal notation. So we will encrypt them with AES, look at the first bit, and these are labels, okay? So we have just binary labels. And we want to learn this mapping from plain text to just first bit of AES output. Okay, and we will learn by, as it is usually done, by minimizing certain objective function. Since our model is parametric, we will consider a so-called empirical risk or training error, which essentially measures how far is the predicted output from the true output. Okay, so fk(xi), it's the true output, true first bit when AES is applied to xi, and this is the prediction from our model, and we will try to tweak parameters theta to make the difference between prediction and truth as small as possible. So here L is a loss function, and it is important that it is a smooth enough function. So, for example, it can be a squared error, but of course, this is usually done used in regression settings. Here, since it's more like classification, a different loss, cross-entropy loss, is usually used, but it is also smooth with respect to input. So also can be analyzed in the same way. Okay, so we want to minimize this average error across the training sample and hope that the function that will be obtained by the learning algorithm, which is essentially minimization of the training error, we hope that the resulting function h with parameters theta star will work well on new data. Oh, by the way, I think I forgot to mention that we are now trying to learn encryption, not decryption. Okay, so we simplify as much as possible. So let's try to learn in forward direction, like encryption. Okay, but of course, since AES is one-to-one, all this reasoning can be applied to AES inverse. The only thing which is important will be the result analogous to result of Liu, which would say that two outputs of AES inverse are also close enough to uniform random. Okay, so how do we usually solve this minimization task? Well, this is the standard approach in deep learning. Essentially, all those success stories, which you know, those AlphaGo or AlphaFold or ChatGPT or self-driving cars, or so they're all initially pre-trained with this algorithm or its variant. Okay, so the algorithm is gradient descent, which is a very simple thing. You initialize theta by randomly picking a point, and then you make a small step in the direction opposite to the gradient. Well, gradient gives you the direction of steepest ascent, but since you want to minimize, you make a direction opposite to the gradient. Then you make a tiny step, and then one more. Like you repeat this process till you end up in one of the holes. And of course, the hole doesn't have to be the global minimum. There is no guarantee. But we usually in deep learning expect that it will end up in a nice hole, nice enough, such that the learned function will generalize well to new examples. Okay, so and then the main result. Okay, our main result. So if we use this near orthogonality, our lemma, and if we apply Boas-Bellman type inequality. Oh, wait, one second. So here I wrote L subscript k because apparently this training error depends on the key of AES key, and of course, when key changes, labels will change. But when labels change, this surface will change, right? The optimization landscape will change, and of course, when for different keys, let's say you start at some point, and for different keys, we expect the gradient to point to different directions, right? If we change key, but gradient always points to the same direction, let's say at the beginning and then subsequently, then of course we cannot hope that we will learn something meaningful, right? Because how is it possible that if we change key, if we change the target function that we aim to learn, at the end of the day, the trajectory, the path, the gradient path, if it's the same, then of course we will end up at the same place. And how is it consistent with this algorithm to distinguish between different instantiations of AES? Okay, so this is the result. We use the near orthogonality and the Boas-Bellman type inequality, which is generalization of Bessel's inequality, and we can prove this result, which was inspired by Shalev-Schwartz work. So we can show that the gradient of the training error has tiny variance when key is sampled uniformly at random from Boolean hypercube. We can make like by having enough sufficiently many rounds of AES, we can make this epsilon arbitrarily small, and this is already small because n is something like 128. Now, what is this c? It's a constant that upper bounds the squared norm of the gradient of the model of the neural network, because our neural net it's also I mean, it has the parameters, and the gradient here is with respect to parameters. Yes. So yes, this is assumed to be not large, and then the result is small, and it means that gradient doesn't vary much when you sample. When you use different keys, the gradient doesn't deviate much from its average. And of course, just as I mentioned previously, this prevents from learning successfully AES. In fact, this can be formally shown. Okay, so here by variance of the vector, here I mean actually square deviation in the norm, in the Euclidean norm. From the average gradient. So there is a work by Shamir and others in 2000. Only Shamir, sorry. And if we plug in this bound in Shamir's one of the Shamir's results in his paper, then we can formally show that gradient descent will fail to learn any single bit of AES unless the number of iterations in gradient descent is exponential in n in the key length. Also, this result is universal in the sense that regardless of which class of models is used, as long as they are parametric and trained by gradient descent, learning will fail. And if we replace AES with AES inverse, we can show that also gradient-based learning, deep learning, will fail to learn decryption. Okay, something that we wanted initially. Few experiments. Of course, we showed that learning fails, but why don't we try? So we generate a training sample as follows. we take plain text x1, encrypt with AES, key is fixed,
Okay.
and we pick.
Sorry.
Is it okay?
Yeah, we have a bit of an unstable internet, but I think it should be fine. You can still...
Okay. So basically, this is ciphertext, like encrypted x1, and we take the first bit of the plain text. So basically, let's try to learn decryption. Okay, like first bit of decryption. So this is our training sample. We experimented with three architectures of neural network. Here, sizes of layers are displayed. So, of course, each of the neural networks takes 128 bits as input, and then these are the dimensionalities of intermediate layers. And the output, yes, it's just a single bit. So once we train them and then evaluate on held out data, these are the results we get. Okay, so say this depth 1 neural network can somewhat fit the training set, but on new data, on new examples, all of them are not better than coin flip, like not better than guessing the first bit of AES just by flipping a coin. So then we took this kind of most successful architecture, the one hidden layer neural network, and projected these 2048 dimensional hidden representations to 2D plane to see what's going on. And here, shapes and colors correspond to classes. So we have only two classes, right? 0, 1. This is the first bit of the plain text, and the representations here are all mixed. They are not separated. Of course, one may think, oh wait, but we projected from high dimensional space to low dimensional. But if they were, if they were well separated in high dimensional space, we know that PCA is a linear method of projecting. So if they were linearly separated in high dimensional space, then they would still be linearly separated on 2D plane. But this is not the case. We don't see this. And I mean, this is because PCA has certain optimality, right? In the way it projects. And yeah, we don't have separation between classes, neither on training, it's a little bit separate, right? This according to this 061. On test data, no separation, so they are all mixed. Yeah, that's all. Thank you for your attention.
Okay, any questions? Here or the virtually on in the audience. Okay.
Igor.
Oh yes.
Igor, you are muted.
Yeah, can you hear me well?
Yes.
Yeah, so the optimality that PCA uses is it goes in the direction of the highest variability, right? And so
right.
it uses the correlations to do that. So just a quick question. This means basically that the correlation, right? So I'm thinking in terms of variability. There is no correlation structure whatsoever, then, right?
Right. So
so I think sorry, this is the only criterion that PCA uses, right? And so it would be just that, right? No correlation.
Yeah, I think of PCA as finding. So since we're projecting on 2D plane, it means we're using two principal components, right? The first one, like if we really had two clouds of points in high dimensional space, in that 2048 dimensional space, which are linearly separated, right? Then the first component is essentially the direction that connects the centers of these clouds, right?
Right, the vector that would be between the
And
right.
then the second component is yeah, orthogonal to that. So if they were really separated in high dimensional space, after projecting them to the plane, they should have remained separated, right? So
Yes,
we had this feedback from the reviewer, like, oh wait, you're projecting from 2048 dimensional space to 2D, then can't the structure be lost, the separability? Well, not really. If they were separated, then they would still be separate, but it's not the case. So it means they were not separated in the high dimensional space.
Thank you. Yeah.
I have a couple of questions, in fact.
Yes, yes.
So you try to attack the full round AES. Have you tried to attack a reduced round to see?
Yeah,
like
this is what Martin did with his group. He tried to learn, say, just one round, and then just like half of the round. Like let's say we want to learn just mixed columns, or just shift rows, or just S-box, right? They're all sort of parameterized because key is added, right? Pseudo random key is added before each round. So yeah, I mean, unless he reduced the input, basically the key length, to something very small. Okay, so he tried to kind of create artificial small, like reduced AES version, and those were partially successful, yes. But for when it came to 128 bits, even single round is not learnable. Fortunately or unfortunately? I think fortunately, right? Because this is failure, but on the other hand, this is good news for security of AES.
Yeah. What about also trying to use these learning methods to, in fact, improve some of the existing attacks? So you use them in conjunction with differential or linear cryptanalysis, for instance, or other attacks to find I don't know, good differential characteristics, like basically good plain text hypertext pairs that that correlate well with the input and output.
Yeah, I think that's possible direction. Actually, Martin, at the end of the project, so the project stopped in July, and I remember that closer to the end, he was trying to do something in this direction, where he looked at differences of inputs and see how they correlate with outputs. But there was nothing successful as far as I remember. Also, yeah, he tried to use machine learning to try to capture these correlations, but wasn't successful. And one thing which was sort of successful was deep learning based side channel attacks, but of course that's a different paradigm, right? We cannot assume usually that we have access to those signals, side signals.
Okay. Any other question?
We'll have a question on this concentration of gradient result. Can you write the R as a function of N in this theorem?
R as a function of
N.
N.
N. Ah, you mean like bit length?
Yes.
Well, actually, this n, I think it's a bit strange that I use n everywhere. In fact, it doesn't vary, right? It's just 128 for AES. It's the input length, right? It's not key length.
Yes.
Epsilon is a function of R, of the number of rounds. In fact, this epsilon is that guy from Liu's result. So this is the epsilon. This divided by 6. Wait. R, when R, like when you have 6 R rounds in AES, this is the epsilon. Okay.
Yes.
And yeah, this it's decaying, well, exponentially, but still slow. As I told you, R should be unnecessarily large to have, according to this theorem, reasonable security. So yeah, there is room for improvement. I mean, if this can be lowered significantly, that's of course will be good.
Yeah. So what I was saying is, if you express epsilon, if you express R in terms of epsilon and epsilon in terms of n, your theorem can be expressed as the inverse of 2 to the input. That's why 2 to the n or something like 1 over 2 to the n or something like that.
So you can find R, and R should be something like 9,000. So with 9,000 rounds, your 2 epsilon will be in this order.
I see. Okay.
So yeah, I know this is a bit useless result, but I mean the approach is like this. Okay, so we heavily depend on Liu, right? And we tried to go into Liu, but it's was sophisticated for us at that time, so we decided not to try to improve, just use it. But yeah, once anyone gets better better closeness to pseudo randomness to randomness, yeah. Here, if I think actually one recent paper tried to improve this, but I forgot to mention in this loose result, all round keys are assumed to be random, which is again not the case in reality, right? They're pseudo random. They're generated in deterministic way from with the key scheduler, right? So there is one more hidden assumption that is not realistic. But then there was a paper. I have it here on my desktop. I want to read it, but cannot find time. So this one extends, well, not extends, but follows up the result of Liu and gives a better bound, but under the assumption that S boxes are random and independently chosen. Okay, so one more deviation from reality.
Okay. Any other question? So I think we have a department meeting soon. So thank you very much, Zhenisbek. It was a very nice talk. Very nice to see you also, Igor. So nice to see you, all of you. So thank you again.
Thank you. Bye.
Thank you.